It's time to put everything we've discussed so far about the photoelectric effect into the mathematical form that you'll actually use to solve problems and represent situations numerically. So, as we've discussed at length in the last few scenarios that have been presented, when the electron is ejected, it will have some maximum kinetic energy. Now, here's a note about this notation. So, remember that we said that the electrons start off in that potential well. That's a pretty sharp potential well. They start off in the potential well, and the photons need to eject them out of this potential well, so it takes some energy to get them out, and then the rest will go into their kinetic energy. Now, the reason we say we discuss the maximum kinetic energy in the photoelectric effect, this is the maximum we measure, so remember we discussed how to measure this using the backing voltage, is that not all, and I'll put this other bit of notation, the depth of this well was phi, the work function, not all electrons in the metal have the same value of phi, the same work function. This is essentially the minimum amount of energy required to remove an electron from the surface. However, depending where the electrons are, they may be, say, at a deeper layer of the metal, a bit further in, they may require more energy to leave. So those electrons may not be ejected at the same, with the same energy photons. However, the most energy we can possibly get, the most kinetic energy we can have, is going to be if we started off with an electron with the minimal work function, the bare minimum amount of energy to remove it from the top layer of the metal. It's really easy to strip off compared to, say, deeper electrons. So that amount of kinetic energy is going to be, so we can start writing this, it's going to be how much energy the photon had. So we know that E is hf, or you can also write this hc over lambda. So the kinetic energy of that electron is Planck's constant times the frequency of the electron. However, we've got to take away the work function. We've got to take away that amount of energy that we needed to, the amount of negative electric potential we needed to overcome to eject the electron. So now we've got something very useful. This equation gives us a nice representation of what's happening in the photoelectric effect. So this is how much energy, kinetic energy it ends up with. So that is the energy of the photon minus the work function. The energy required to remove that electron from the surface. So you might notice something about this equation. It is in a pretty typical format for a linear equation. We have, this is sort of the same basic structure. If plotted correctly as y equals mx plus b. So let's think about what we would need to graph here. So if you make a graph, and we'll draw this over to the right here, and on the y-axis you plot the maximum kinetic energy, Ek max, and on the x-axis you plot the frequency of the incoming photons, you will get a nice linear equation. Something like this. And so if you did this experiment and you plotted these quantities, so for example, say you were to change the frequency. So for several different frequencies, you use the backing voltage to measure the maximum kinetic energy. You would get a series of points, and if you connected them up, you get a line like this. And let's discuss briefly what these features would be. So obviously, y is our maximum kinetic energy. F is our x value. The term multiplying our x-axis is h, and that is in the place of our gradient in the our gradient in the conventional linear equation format. So that means our gradient is going to be Planck's constant. So that's very useful. You can make an empirical measurement of Planck's constant just by performing the photoelectric effect and measuring the maximum kinetic energy for different values of frequency. And if you do that and you find your gradient after graphing this, that gradient will be Planck's constant. We can also see that in the place of b, which is our y-intercept, we have the work function, or minus the work function in this case. Now, you can probably see just geometrically what's going to happen here. Now, let's have a look at this point where it touches the. Let's first have a look at this our x-intercept here. Now, it doesn't make sense. We're not going to measure values lower than a zero kinetic energy. So at some frequency, and we call this the cutoff frequency, electrons are no longer ejected. So there's no kinetic energy at all. They just don't leave the metal. And that happens when the energy of the photon, this point will be when the energy of the photon is exactly equal to the work function. So that would, in theory, give zero kinetic energy. They can just break out of the potential well. They can just reach the top of this potential well, but there's no energy left for kinetic energy. And if we go less than that, then the energy of the photon is less than the work function, in which case they definitely can't escape. And we don't actually measure any electrons arriving, and we don't measure any photocurrent. So beyond here, so sort of going back, we could extrapolate this, but we can't measure values back here necessarily because there is no, at this point there just isn't any electrons being ejected. But if you do extrapolate this, this line back and you look at this y-intercept, that value down there is minus phi. That is our work function. So all our key values that we might be interested in, so cutoff frequency, that's the minimum frequency that will eject an electron. The y-intercept, if we extrapolate back, that's our work function, so the amount of energy that is required to remove the electron from the surface. We've got Planck's constant in our gradient, and of course we could figure out the kinetic energy for a different frequency. All of the important quantities and values that we're interested in are very nicely represented by this equation and the graph of this equation. So keep that in mind, because this will be a very useful problem-solving tool when working with the photoelectric effect.